I welcome you all in my series of a lecture about the generation of microwave signals. This is my fifth lecture. We will be observing the another one device that is a magnetron. Magnetron is used to generate a microwave signal. It is an oscillator type of device. But here, the electric, then what is the difference in between the reflex klystron and magnetron? The first difference is a magnetron is a high power generating device. So it can be used in a radar. It was invented during the Second World War and it can be used in the radar. Then the second thing is that is the whatever the electric field and the focusing magnetic field, they are perpendicular to each other. Or the electric field is having in a transverse direction, magnetic field is in an axial direction. So this is a cross field type tube, or we can call it as an M type tube. Then it can be used in amplifiers. It can give in a very high power, high output signals. Okay, these are the some comparison points in between the reflex klystron and magnetron. Now we'll see this magnetron, how it works in detail. Now first of all, magnetron is an oscillator that will generate a high microwave power required in a radar, that will generate a high microwave power required in a radar. Its power output is in a nearly about 40 to 60 megawatt, and similarly the efficiency is increased from 40 to 70%, and it can be used in a radar transmitter or it can be used in a microwave ovens. It is working, it is giving in a high power at an ISM band. In some countries 915 megahertz is an ISM band. In some countries, 2.45 gigahertz is an ISM band. 2.45 gigahertz is an ISM band. So it will give. It can be used in industrial heating, or it can be used in a microwave ovens. It is in a domestic applications, or it can be household homes, or to prevent or that is the moisture or the water is the main uh, culprit which destroy the food and grains. So to dry these food atoms and the grain atoms, we can use this oven. Now the construction of this magnetron. Magnetron consists of the cavity that is the cylindrical klystron. It is shown at the center. Like cylindrical klystron is there. It is indicated by cylindrical cathode is there. It is indicated by an letter K. Now this cathode is surrounded by the number of anodes, or it is surrounded by a cylindrical anode. This anode consists of a number of reentrant cavities. The circles which are shown, that are the reentrant cavities. There are many number of reentrant cavities inside the anode. Now these reentrant cavities, when they are supplied with a high voltage signal, there is some noise is generated in the reentrant cavities, and this noise is in the form of RF field. So RF field is present in the reentrant cavities because of this noise. Similarly, when we supply a high negative voltage to the cathode, then the cathode will emit the electron. And if you see, there is a V0 voltage is supplied in between the cathode and anode. So that will create, or that will make the cathode to release the electron or emit the electron. That will make the anode uh, re-enter cavities to generate a RF signal. Similarly, it will generate an electric field which is transverse in direction. Then along with this, there are two magnets. One is kept at the top and another one is kept at the bottom of the device, which is not shown over here. Now these two magnets will generate a magnetic field that is indicated by B0. If you see the direction of magnetic field, that is an axial one. So magnetic field is in axial direction and the electric field is in a transverse direction. So we can call it as a cross field tube or AM type tube. So what are the advantages of cross field tube or AM type tube? They will control the movement of electrons or a bunch of electrons in such a way that can exert a maximum energy to the RF field, and the force which is generated, combined force which is generated due to the electric field and magnetic field, is called as Lorentz force. So this Lorentz force is responsible for the movement of the electrons, and giving the maximum energy to the RF field. Now see here how the processes are takes place. As we have seen, magnetic field is in an axial direction, electric field in a transverse direction. There are many anode cavities which are connected to each other by the stripes. We can see the stripes connecting the cavities also. Now see, when we give an electric field, then the cathode will emit the electron. This emitted electrons comes in contact. They will move through the space in between the anode and cathode. When they move in between the anode and cathode, they will come in contact with the RF field which is present inside the cavities. Now this RF field will do the due to the RF field, the velocity modulation of these electrons will take place. That is, whatever the electrons coming in positive contact within a positive half cycle, they will get accelerated. Negative half cycle, they will get decelerated. As a result of this, the density modulation takes place. That is, the bunch of electrons are formed. As we have seen earlier, all these processes in detail in my lecture number 2. So the bunch of electrons are formed, and this bunch, as the bunch are formed, they will tend to give their kinetic energy, and this outputted kinetic energy is catched by the RF field which is present inside the cavity. Now all these RF field present inside the cavity can be connected to each other with the help of an stripes, and it can be taken out by using an output coupling loop using a coaxial line. Like this it can operate, or it will carry all these 5 processes. Now see how this, I have told you about an electric field and a magnetic field. They are acting simultaneously on this in this magnetron. Now what is the effect of this electric field and a magnetic field, that we will see. The force exerted by an electric field and a magnetic field combined, that is called as a Lorentz force. Now the Lorentz force which is responsible for the movement of an electron or the path of electron in between the anode and cathode, how it affects, you can see. Here the path of electron is shown by using a different colored arrow. That is, first of all, when the Lorentz force is the minimum or there is a zero force, we can say like the electron is taking a path indicated by a blue color. So this blue color path is directly, the electron comes out of cathode, that will directly move to the ion. Then second, that is, if we increase a magnetic field by a little amount, then it will take a little bit curved path as shown by a green color arrow. Then if we want to exert a maximum energy to the cavities, we should take the curved path same as that of indicated by a violet color arrow. That is, the electron should move at a 180 degree from one cavity to another cavity. So that one that can be the field, magnetic field at which it takes place. That is called as a critical magnetic field. So whenever the magnetic field is equal to critical magnetic field, it will take a violet color path. So this violet color path is indicated in the figure. Then the another one, that is, if we increase the magnetic field above the critical field, then the red color path is taken place by an electron, and electron will move for a larger distance, and that is not advisable. That will come back to the cathode and that will heat the cathode. Similarly, if we go on increasing again, then the many times or many hops of electrons are taking place. Electrons will come out of the cathode, again they will go back to the cathode immediately, and that will heat the cathode and that will heat the device. That is also not advisable. So always it is required that we have to maintain the magnetic field equal to critical magnetic field, and this device can be mainly used in the radar as well as it is used mainly in the ovens. This is about a magnetron. Thank you.